So let's look at this example that I told you guys to try. This is sort of a radical function. We're going to start by doing our domain of this function. So we try to think about what's not allowed for the function. So what I'm going to do is I'm going to rewrite this just to kind of look at it in a different way. So this is the cube root of x squared times the cube root of 6 minus x. You're going to notice that because both of these are the cube root, we're allowed to take the cube root of positive and negative numbers. So technically there's no issues on my domain. We're allowed to have all real numbers. Okay, so I'm going to highlight that. That's kind of my first characteristic. B, we want to do intercepts. So again, to find x-intercepts, we set y equal to 0, solve for x. So my expression is already factored. So what I'm going to do to find my x-intercepts is I'm going to try to think about what makes this part of my function 0. So 0 would be, when x is 0, the whole expression is 0. What would make this expression 0 would be x equals 6. So those two happen to be my x-intercepts, 0, 0, 6, and 0. Now because 0, 0 is already an x-intercept, that means that my y-intercept has to be 0, 0. But if you're not convinced, 0 to the 2/3, 6 minus 0 to the 1/3, which is just 0. So my y-intercept is also 0, 0. So there's my intercepts. Part C, we would like to do symmetry. We want to figure out, does our function have any sort of symmetry? In order to do that, we need to compute f of minus x. So I have minus x to the 2/3, and then 6 minus a negative x to the 1/3. And this simplifies. So if I do negative x squared, I get positive x. So this would be x to the 2/3. And then this part would be 6 plus x to the 1/3. Now the problem here is that this sign has changed, but the sign in front of the 6 hasn't changed. So there's no way to ever make this look like the function or the negative of the function. So we have no symmetry. Let's summarize that symmetry. D, we're going to do asymptotes. Now again, at some point you want to start sketching the information. I'm going to do it after I'm done my asymptotes. So for the vertical asymptotes, there is no denominator. So that means there's no vertical asymptotes. We don't have to make this more complicated. So no vertical asymptotes. Horizontal asymptotes, in order to determine them, we need to do two limits. We need to do the limit as x approaches infinity of my function, which is x to the 2/3, 6 minus x to the 1/3. So let's evaluate this. I have a large number squared, which is a large number. Cube root a large number is a large number, times 6 minus a large number is negative infinity. Negative infinity cube rooted is negative infinity, which means that this result is negative infinity. So as x gets large, y is getting large in the negative direction. Limit as x approaches negative infinity, x to the 2/3, 6 minus x to the 1/3. So negative infinity squared is large number, positive large number. Cube rooted is infinity. 6 minus a minus infinity is plus infinity, and then cube rooted is just plus infinity. So there are no horizontal asymptotes. But again, this information is still really valuable for us because it kind of tells us on the graph the behavior of kind of what's happening. So I'm going to make a category for first derivative stuff. Kind of a large category for that. I'm going to make a category for second derivative stuff, and then I'm going to have some space here to start sketching my graph. So on my graph, I know that one of my intercepts is 0, 0. One of my intercepts is 6 and 0, 3, 4, 5, 6, 7, 8, 9, 10. I'm going to label the 10 way over here so that it doesn't affect my ability to draw the graph. 1, 2, 3, 4, 5, 6. Whoops, I didn't want to do that. 1, 2, 3, 4, 5, 6. So there's my asymptotes. Furthermore, I know that there's no symmetry, there's no kind of characteristics of the graph that are reflections of one another. But I do know that as x goes to infinity, y goes to negative infinity. So my graph has to be coming down to negative infinity. As x approaches negative infinity, my graph is getting large, so that means it has to go up on this side. So that's all the information I have so far. Let's just continue with our first derivative stuff. Whoops. First derivative stuff, which means I have to actually take the first derivative, find my intervals of increase, decrease, and all that sort of stuff. So there's my original function. I need to take the derivative and set it equal to 0. So y prime equals, this will be product rule, 2/3 x to the minus 1/3, derivative of the first, times the second, plus I leave the first one the same. When I do the derivative of the 6 minus x term, it's going to be chain rule. So I do 1/3, 6 minus x to the negative 2/3. The derivative of the inside is negative 1. So first thing I'm going to do is kind of clean this up a little bit. And how I'm going to do that is I'm going to put the numbers together at the front of each term. So this will stay at 2/3. And this one will get to be minus 1/3. That's the orange stuff. I'm going to write this term second, which is kind of the one with the base of x. And then I'm going to write the 6 minus x term third over here. So 6 minus x to the 1/3, 6 minus x to the negative 2/3, and then we have our minus sign separating the terms. Now I'm going to ask myself, what is in common between the terms? So let me use red again. I have a 1/3 and a 2/3. So out of these two, what's in common? I'm going to factor that out. I'm going to factor out a 1/3 because they both have the 3 on the denominator. When I look at the next term, and I've switched the colors around on you here, my apologies. So which is the smaller exponent? X to the negative 1/3. The negative 1/3 is the smaller term, so I'm going to factor that out of both of them. And in green, I'm going to look at these two terms and I'm going to factor out the smaller term. Now this was that factoring we were practicing earlier, and we're trying to like simplify my expression. So if I take out a 1/3, I need to multiply this by something to get me 2/3, so that would have to be a 2. I have x to the 1/3, x to the 1/3, that will cancel out. I need to have a 6 minus x term to the something over 3, so that when I add together this term and this term, I get a 1/3. And you'll notice if I put a 3 over 3, 3 over 3 minus 2 over 3 will give me the 1/3 that I had started with. Minus, now x to the 2/3, I'm going to do the same thing, x to the something over 3. Let's do it in green. Something over 3 plus negative 2 over 3 needs to give me the original 2 over 3 that, over here. So negative 1/3 plus something over 3, but you'll notice if I put a 3 over 3 here, 3 over 3 minus 1 over 3 will give me that 2 over 3. And then I've factored out the 6x to the minus 2/3, so that's what's left on the inside. Clean this stuff up, 1/3. I'm going to move the x to the 1/3 on the bottom. 6 minus x to the 2/3 goes on the bottom. So I'm going to just kind of put an arrow that moves those to the bottom. I'm going to get rid of this one, but this whole term sits on the numerator. So it's going to be 2 times 6 minus x minus x. Now I'm going to do one final step to clean this up. So y prime equals 12 minus 2x, and then another minus x makes 12 minus 3x over 3x to the 1/3, 6 minus x to the 2/3. So again, I can do one more cleanup step. I'm going to factor out a -3. I'm going to be left with x plus 4 divided by 3x to the 1/3, 6 minus x to the 2/3. And then I'm going to do one more cleanup step. So this 3 and that 3 will cancel each other out. So now I'm going to circle this. This is my simplified first derivative. I'm going to highlight it because that's kind of the key as part of my solution. We need to find where the derivative is equal to 0, which will be coming from the numerator. X would have to equal -4. We're going to ask ourselves, where is y prime does not exist? This would come from the denominator equaling 0. Now, one thing you want to notice is my domain of the function was all real numbers, so these are part of my domain. So that means they're a point where the derivative doesn't exist, but there was some sort of continuity of that point in the original because my domain was all real numbers. So part of my domain, I can classify these as maxes, mins, and so forth. So here's my number line. Whoops, why am I writing y double prime? So this is y prime, and we're going to say something about y. So -4, 0, 6. Let's test this section. So when x is -5, my numerator would be -5 plus 4, which is negative. Negative and negative make a positive. On my denominator, -4 to the 1/3, that's a cube root of a negative. Now this term, you'll notice, is always positive because when I square anything, it's going to be positive. So I'm really going to kind of omit that out of my thinking and just focus on these parts. If I take a number like -1, my numerator will be negative. My denominator will be negative as well because the cube root of a negative is negative. So this will give me an overall positive result. If I sub in x is equal to 1, my numerator will be negative. So this will be a negative value. And when I type in 7 plus 4 is 11. The numerator will be negative, denominator will be positive. So this will overall be a negative result. Okay, so this tells me my function is decreasing, increasing, decreasing, decreasing. Let's summarize that result. F of x is increasing on -4 to 0, and that's actually it. Because f prime of x is greater than 0, you'll notice I switch between f prime and y prime, doesn't matter. F of x is decreasing on -infinity to -4, union 0 to 6, union 6 to infinity. Now let's consider local maxes and local mins. So we're looking for sign changes. Oh, let me write because f prime of x is less than 0. So we're looking for sign changes from plus to minus. So this is going down, down, and then up. So there's a local min. Up to down, local max. And then there's no sign change on that last section. So local max at 0 comma blank. We know that value will be 0 because it was the y-intercept or x-intercept, but you can figure it out if you need to, because f prime changes from positive to negative, and local max at -4 comma blank because f prime changes. Oops, that should be a min. I already said max from negative to positive. Okay, so let's take this information and transfer it to our graph here. Oh, let's undo that. Okay, let me just get my graph. I'm going to move that down. Okay, so let's take away this arrow. Okay, so at -4, I want to sub it back into my original function. So when x is -4, y is equal to, let's look back, -4 to the 2/3. So that's squaring 4, which is 16. So that's the cube root of 16. 6 minus a -4 to the power of 1/3. So that's 10 to the 1/3. 6 minus a -4, so that will be cube root of 10. And then we'll just leave our result like that. You would need to kind of know where that y-coordinate is. You would have to use a calculator to get that decimal, or you may have to approximate. So let's transfer that information onto our graph. So there's a local max at 0, 0. So we know, whoops, did I make a mistake here? So my sign at 0 switches from positive to negative. Minus, plus, minus, minus. Let me just refer to my solution key here for a moment. Oh, and I've made a mistake. Minus x plus 4. So we have to go back here because I've kind of made a mistake. So when I factored out a -3 from the numerator, I get x minus 4. And I wrote x plus 4 here. So I need to come back and fix that to a negative. So this is why it's really, really important you don't make errors like I just did. Because when you do, it just changes your answer very quickly. So let me show you how I realized I knew there was a mistake. It was really tricky to think how this could be a local max without coming back up here and crossing the axes to go back up. So I knew I made a mistake. So let's go back and fix this mistake. So my number line has to have 0, 4, and 6 on it. So now when I solve the numerator equals 0, so x minus 4 would have to equal 0, which means x would have to equal 4, and my denominator doesn't change. Now when I analyze these signs again, when I sub in a number like -1, that would give me -5. That would switch to a positive, but -1 would also make that negative, so this result still holds. This negative sign is still true. If I test a number like +1, 1 minus 4 is negative, negative and negative make a positive, so that's a positive. And then my denominator is also positive, so that result still holds. This is still going to be positive. When I test a number like 5, my numerator will be negative, my denominator will be positive. And when I test a number like 7, my numerator is negative and my denominator is positive, so everything holds. Now we just have to change kind of our interval slightly here. Function is increasing on 0 to 4. Function is decreasing on -infinity to 0 union 4 to 6 union 6 to infinity. Same reason. So just be very careful, like I was. If something looks like it's not making complete sense, go back and check it. Now let's check here. Now at 0, my sign is going from negative, to positive, which means it's going down first and then up, which means a local min at 0, 0. So I need to change that word to minimum at 0, 0 because the sign switches from negative to positive. And now at the other one at 4, there has to be a local max at 4 because it goes from positive to negative. So let's say positive to negative. When x is equal to 4, let's put a positive 4 in those. I had a feeling something was wrong, but now I figured it out. So this would be the cube root of 16 still. 6 minus 4 is 2, so this would be the cube root of 2. So this would be the cube root of 32 if you wish, but you could just leave it as cube root of 16 and cube root of 2. Now if I do that on my calculator here, just to quickly get a rough idea, this is approximately 3.17. So you know that. So now when I go to my graph, this will be a little bit making more sense. So there has to be a local min at 0, 0, which makes more sense because the graph can go like this, and this will go up. And then on the other side, at x equals 4, there has to be a local max. And the max will be approximately 1, 2, 3, 4, at approximately a y value of 3. So if I change my axes to 1, 2, 3, this will be at approximately 3.17. So kind of up there. Okay. And now there's a local max here, so the curve has to go like this. It probably will go through my intercept and come back down. So that's my prediction of what is happening with the graph so far. But again, let's check some information. So it's only increasing from 0 to 4. This sort of has, this part of the graph has like a negative trend. So that's decreasing. It increases up to the max, decrease, decrease for the remainder of the graph. So that part sort of matches up. I'm going to get rid of that. And then there's my local max and min. So now what we're going to do is do our second derivative information and then add that to our graph. So this is step E, I believe. Wait, oh, no, F we're on. So my last step would be my second derivative stuff. Okay, so second derivative stuff. My first derivative simplified was negative bracket x minus 4 over cube root x cube root 6 minus x squared. So let me actually rewrite this slightly differently. X to the power of 1/3, 6 minus x to the 2/3. So now the only challenging part of some of these questions is to make sure that your derivative is correct. If you can do your derivatives correctly, that's kind of the big key that you need to have. I'm going to move this graph down now so that we have lots of space to work. Now what I'm going to do is I'm going to let you work out this derivative, and I'm going to show you how to find the second derivative kind of easily. So as you're working, you know how to check your work. Okay, so what we're going to do is we're going to go to the internet. We're going to go to Wolfram Alpha, and it's going to help us make sure that we do our second derivative correctly. So what we're going to do is we're going to type in our first derivative as a function, so y equals, now you got to be careful here, so I'm going to go bracket negative x minus, negative x plus 4. So I want to make sure that when I'm typing it in, I'm trying to type in the least amount of function. So I distributed that negative on the top. My denominator is going to have a bracket to start off with. X. Now you have to make sure you're using the same size x's. If you're using lowercase, stay with lowercase. X to the power of bracket 1 divided by 3, end my bracket, times, and now we have bracket 6 minus x to the power of bracket, bracket 2 divided by 3. And then what you want to do is hit enter to make sure you've typed it in correctly. So you'll notice that it didn't read this correctly because of the hat symbol. So retype it in. Make sure that the very first thing you see is that the function was typed in correctly. So negative x plus 4 is my numerator expanded out. Cube root of x, and then 6 minus x to the 2/3. All the variables are lowercase. What you want to do is look down to where it shows you the second derivative. And if we hit this more button, it might, oh no, not there. Okay, let's actually type in find derivative. Usually works. So there is my derivative simplified for us right there. So what we're going to do is kind of write this down so that we don't forget it. And then what you want to do is make sure that when you do all your work to do the derivative, you can go to it. Now, if you go here, step-by-step solutions, sometimes it might show it to you. Sometimes you might have to pay for it. So if you're not sure, just this is what your goal is to make it work out to. So let's go back in. So this will be negative 8, 6 minus x to the 5/3. And 6 minus x to the 5/3, x to the 4/3. Okay, I'm just going to quickly scribble that down. So what you're going to do is do the work, clean this up. You can come in during a focus session if you need to help simplify this. Negative 8 over 6 minus x to the 5/3, x to the 4/3. And then I'm going to clean all this up. Okay, so you're going to do all the work inside. Your turn. And then this will be the simplified second derivative, provided Wolfram Alpha did it correctly, but we'll be able to tell if they did or not kind of when we look at the graph. Okay, but that's a little trick as you're working to help you with the derivatives, but at the end of the day, you will need to solve all of these questions on your own. Y double prime equals 0 implies there's no solutions, so there's no critical points where the derivative is 0. Y double prime does not exist is at x equals 0 and 6 again, and these are in my domain, so they can still be classified as maxes, mins, inflection points, and so forth. We do our number line with the second derivative, so I will include 0 and 6. When x is negative 1, my numerator is always negative. You can see it's always negative 8. My denominator is, so when x is negative 1, you're doing power 5, and then cube rooting it. This one will be always positive because you're going to do the power of 4 before you cube root it. So we're only going to pay attention to that term right there. So 6 minus a negative 1 will be a positive number, cube rooted. When I type in 1, 6 minus 1 is 5. This will also be a positive number when cube rooted. However, when I start to put in a number bigger than 6, this is going to start to be negative. So this will be negative, negative, positive. So this will tell me my original function is concave down, concave down, concave up. Let's write our sentence. F of x is concave down on negative infinity to 0 union 0 to 6 because f double prime of x is less than 0. F of x is concave up on 6 to infinity because f double prime of x is greater than 0. Now, is there any sign switches? The sign switches from negative to positive at x equals 6. So we're going to say inflection point at 6 comma, and I believe that was an intercept, so 6 comma 0. So we're just going to highlight these because those are part of our solution. Okay, so now let's double check. Up until 0, I should be concave down. Something looks weird again. So decreasing to increasing, local min at 0. Local max at 4. Now the function is concave down, so it should be frowning. So what we need to do is for this curve of our graph, we need to change the curvature of it so it's facing down. So it's going concave down, so this is facing down, facing down. There's an inflection point at 6, so what we're going to do is label it when x is 6, 1, 2, 3, 4, 5, 6. And at 4 and 0, my graph is slightly off. At x equals 1, 2, 3, 4, and 3 point something. Concave down. So you have to watch the curvature carefully. So facing down, now I drew the curvature of this piece wrong. This one needs to be facing down. There's a local max at 4. Okay, then it kind of switches, coming down. So it's facing down all the way till I hit this point. And when I hit that point, it's going to go concave up. So it's going concave down, and then this way it's concave up for the rest of the graph, but this piece is going down to minus infinity. So the challenge with this graph is to make sure that the curvature is correct. So concave down, concave down, concave down, inflection point switches to concave up. Okay. Now what I want to do is I also want to show you on Desmos how you can check your answer. So what we're going to do is we're going to type in our original function, y equals x to the power of 1 divided by 3 times bracket 6 minus x to the power of 2 divided by 3. So you can see that there's this funny shape to the graph. Now it looks like we might have made a mistake because on the left of 0 it's concave up, then it goes concave down, and then it goes concave down. So something went wrong here. Whoops. So it should be positive, negative, negative, positive, negative, negative. Whoops. Let's look back at Desmos. Maybe I've made another mistake here. So let me just make sure I typed in my original function correctly. It should be x to the, oops, that's why. X to the 2/3, 6 minus x to the 1/3. Okay, so that's concave down switches to concave up. The graph is really funny looking. You can see that there's a lot of areas to make mistakes on, so you want to be really, really careful. So let's check my graph now. So it should be concave down, switching to concave up. So my graph is correct, but it is really funny looking. So you just have to be really careful, and you will have to practice this quite a bit. Otherwise, as soon as you make one mistake, everything else is kind of shot for you. So there's my graph. And again, if sometimes things don't make sense, you want to make sure that you kind of analyze things to make sure, does this make sense? My domain is all real numbers. You go back to the beginning and you can kind of check, you know, domain is everything. My intercepts, there's no symmetry, there's no horizontal asymptotes. My infinities are going in the right direction and so forth, okay? And that's that